Welcome to Learning to Engineer. We saw the static error coefficients and hence the steady state error in this video. Now we are going to look at dynamic error coefficients. Before that, why should we learn dynamic error coefficients? Why do we have them? Because we know to find out the static error constants against different test signals and against different types of the system too. So we can quickly find out the steady state error just with static error coefficients, right? Why do we need to go for dynamic error coefficients? This is because for some of the inputs we get 0 or infinity as the error, though we practically know there is no zero error or even infinite error for that matter. There will be a really large error or a really small error which we need to account for when we are designing a control system for any plant or any system. And if it is type 1 and type 2 systems, for a step input we do not have any error at all according to the static error coefficients. But we need to go ahead and analyze this deeply because frankly there isn't a system which has zero error. We need to understand that very clearly. Okay, and another point is the steady state error concept. It uses Laplace transforms. We are finding the E of t and finding E of s in order to find out the steady state error ESS in a static error coefficient. So what happens? This is valid only for stable systems. When the system is unstable, Laplace transform isn't varied because Laplace itself has a e power minus tau s term in it, which makes the system stable. Only for stable systems this is valid. Or in other words, we can say that the system's roots or the characteristic equations roots, or let us say the poles, okay, the poles of the system should lie on the left half of the S-plane. Even if it is on the imaginary axis marginally stable, or if it is on the right side of the S-plane, then it is an unstable system and we cannot find out the steady state error using static error coefficients. And this is valid only for a standard form like this. So basically we have three reasons for not using static error coefficients always. The first thing is it is valid only for step ramp and very parabolic standard test input signals. For other inputs we do not have an answer. The next thing is only for a standard system we have this static error coefficients. For non-standard systems we need to compute and hence this cannot be used. We need dynamic error coefficients in that case. And another important reason is that it is valid only for stable systems. Okay, so for these three important reasons we need to go for a more deeper level of finding the error coefficients, and hence we have this dynamic error coefficients. I am not going to go through the derivation step by step. I am only going to tell you what these coefficients are and how we are going to apply them in order to find out the steady state error. Okay, so in case you want to know the derivation, in case you want to understand more about the derivation or how you get the steady state error, please let me know in the comment section. I will do a video exclusively on the derivation part alone. Okay, so for now we are just going to understand what these dynamic error coefficients are and we are going to solve one problem in this concept. Okay, so let's get started. The steady state error is equal to K naught into R of t. I'll explain all these terms, but I will not go in depth with the derivation. So, okay, if you want to know the derivation in depth, let me know in the comment section, and I'll be answering them soon. Okay, I'll do the derivations video separately in case you want. Okay, so this is the value of the steady state error, and we need to understand that these terms are the dynamic error coefficients. Okay, K0, K1 and K2, these are the dynamic error coefficients, where the value of K0 is equal to limit s tends to 0 f1 of s. I'll tell you what f1 of s is, but for now just have it like this. Okay, and what K1 is equal to limit s tends to 0, the first derivative of s for f1 of s. What is k2? Second derivative. Same thing, limit s tends to 0, and the second derivative of s for f1 of s. Okay, what is this f1 of s? So we are going to understand what is f1 of s with this. Okay, so where does this start? The error term E of s is equal to R of s divided by 1 plus G of s H of s for a closed loop system, for a negative feedback closed loop system. This is the error term, right? So we are going to split that into two. One will be f1 of s and the other term will be f2 of s. Okay, so this is actually split into 1 divided by 1 plus G of s into H of s multiplied by R of s, which is the input. This term is called as the f1 of s and this is the f2 of s. Okay, and so if we derive, we will get the steady state error which we discussed here. Okay, this is just following two steps. Okay, between these dots there are just two steps. Take the convolution and expand by Taylor series and find out the inverse Laplace transform. Okay, so if you follow these two steps, you will get the steady state error like this. So these are the dynamic error coefficients. K0, K1 and K2 are the dynamic error coefficients. Let's solve a problem in this case. Okay, we just need to remember these formulas, and if you want in-depth understanding, you just let me know. I'll do a video on the derivation part too. Okay, so for a system transfer function, let us say 1 by s into s plus 1, which has a unity feedback, and the applied input is 4 plus 60 plus 2 t cube. Okay, find out the steady state error of this system by dynamic error coefficient method. Just with the use of these formulas, you should be able to solve this problem. Okay, so the first step is we have to find out f1 of s. Even before finding k0, we have to find out f1 of s. What is f1 of s? 1 divided by 1 plus g of s into h of s. This is equal to 1 divided by 1 plus 1 by s into s plus 1. Okay, so what is f1 of s? S into s plus 1 will be in the numerator. In the denominator you will have s into s plus 1, which is equal to s square plus s divided by s square plus s plus 1. So this is the value of f1 of s. What is k0? Simple. 0th derivative, or just the limit s tends to 0, f1 of s, which is equal to 0. What is k0? K0 is 0. We will find out k1. K1 will be limit as s tends to 0, the first derivative of f1 of s, which is s square plus s plus 1 whole square. Square the denominator, write the denominator and differentiate the numerator. Which is eventually 1. K1 is 1. What's K2? K2 will be one more derivative of this. That's all. Because it's the second derivative of f1 of s. For finding K1 itself, we found out the first derivative, and now we are going to take the second derivative, which is limit s tends to 0. Just differentiate this further. That's all. The K2 is going to be 2 minus all the s terms will go away, so you will have one more 2 divided by 1, so the value of k2 is 0. So we will only have two terms in this, k0 K1. Even if you find out K3, it's going to be 0. You can just try it out and let me know. Okay, so the steady state error ESS is equal to K0 into R of t plus K1 divided by 1 factorial into R dash of t plus K2 by 2 factorial into R double dash of t. So if you substitute, you will simply get, what is R of t? 460 plus 2t cube. Okay, I'll just write it here. The input is equal to 4 plus 60 plus 2t cube. Right. So this is equal to, so value of k0 is 0, so super. So this is 0 plus what's k1 is 1 by 1 factorial into r dash of t, which is the first derivative of this is equal to 6 plus 60 and k2 is 0. So the value of steady state error is 6 plus 60. Okay, so this is a very simple method, and using this you can find out the error coefficients of any plants. Okay, so consider this system. You have an amplifier and this is the system transfer function or plant transfer function, and you have a load connected to it. So you have a very big G of S and it is a unity feedback system. So for that, first find out the F1 of S, and after finding that, find out the error constants K0, K1 and K2, and find out the steady state error EFS. So what is the input? Let us say you have an input of 6 plus 5t plus 6 t square by 2. Okay, so this is the input, and for this first find out the G of S, next find out the F1 of S, and hence the dynamic error coefficients, and hence the steady state error. So the F1 of S will be 1 divided by 1 plus G of S into H of S, which is 15 into 200, 3000 into 0.2 will be 60. Yeah, 60. So the transfer function is 60 into S plus 1 divided by S plus 2 into S plus 5 into S plus 1. You can simply cancel both of these. What is the plant transfer function? It is S plus 2 into S plus 5 divided by S plus 2 into S plus 5 plus 60. So the first thing is, what is K0? K0 is equal to limit S tends to 0 F1 of S, 10 divided by 60, 60 plus 5 to 10, which is equal to 10 divided by 70. So this is the value of K0. Okay, so similarly, what is the value of K1? K1 will be limit S tends to 0 first derivative of F1 of S, which is equal to square the denominator, and what will be the numerator? Just write down the denominator. I simply don't memorize the formulas for differentiation, because when you try to memorize, you are trying to bore the subject. Okay, the subject will be very boring to you. So I'll just remember it like this: square this denominator, write the denominator, differentiate the numerator, minus, write the numerator and differentiate the denominator. This is how I differentiate. Maybe whichever is convenient to you, you can use that. Write the denominator multiplied by differentiation of the numerator, which is going to be just 5 into S plus 2 plus 2 into S plus 5. I need even more space, minus, just write the numerator. So what is going to be K1? It's going to be it's a 0. So 5 2s are 10. 10 plus 60 is 70. 70 multiplied by 5 2s are 10 plus 5 2s are 10, minus, you have again 5 2s are 10, and then inside the square braces it will be 10 plus 10. 10 plus 60, 70 square. So 7 7 is 4900. which is equal to 0.244. Okay, so this is K1. Okay, and similarly find out the value of K2. Okay, so now what is the error coefficient? K0 1 by 7 into R of t plus 0.244 into R dash of t. Okay, and the next term is K2 into R double dash of t, which I've left for you to find out. What is K2 into R double dash of t? You're just going to find out and let me know in the comment section. Okay, so it is 1 by 7 into 6 plus 5t plus, okay, 6 by 2 is 3, right? I'm just going to put it like this, plus 6t square plus 0.244 into the first derivative, it is 5 plus 60 plus K2 into R double dash of t. Again, a pretty simple technique, but you just need to be patient and do the differentiation part. Okay, so this is how you deal with dynamic error coefficients. Okay, so do let me know your thoughts in the comment section, and if you have any doubts in this topic, you can let me know. Thanks for watching. Do subscribe to my channel and ring the notification bell so that you will have a notification on your mobile phone when I publish my next video. Thanks for watching.